You re-standing here upon our quiet earth, perhaps gazing at the stars on a clear, dark night, feeling a sense of isolation in the vast cosmic ocean. But what if I told you that you are, at this very moment, not truly isolated at all? What if you are constantly immersed within a profound cosmic communication network, a gentle stream of whispers from the universe's most distant and dramatic corners? Now, imagine, if you will, invisible particles traveling at speeds almost unimaginable, nearly the very speed of light itself. These tiny, silent messengers are reaching us right now, gently passing through everything around you, and even through you. We call them cosmic rays. They are not merely stray bits of matter. They carry profound secrets, etched into their very being, secrets from stars that have exploded in spectacular fashion, from galaxies that hum with incredible energy, and from phenomena that push the very boundaries of our understanding of existence. They offer us direct clues, like subtle brushstrokes on a grand cosmic canvas, revealing the universe's most extreme and awe-inspiring events. Tonight, let us gently unfurl this cosmic tapestry, wharf, and listen to the messages whispered to us from beyond our solar system. Right? Allow your mind to drift, perhaps to the sensation of a gentle rain falling, softly touching everything in its path. Now imagine a similar continuous shower, but one composed not of water droplets, but of particles so infinitesimally small they are utterly invisible to our eyes, so swift they traverse vast distances in the blink of a cosmic eye. These are the invisible cosmic bullets, a constant, gentle barrage, hailing from distances almost unimaginable, from times long, long ago. They are a fundamental, yet often unseen, part of our cosmic environment. These are not just any particles. Oh no. They are the cosmic rays, and within their silent journey lies a profound narrative, a collection of stories whispered from the universe's most violent, most energetic frontiers. Think of them as tiny, tireless messengers, each carrying a fragment of information, a subtle hint about the grand, dynamic processes that shape the cosmos far beyond our quiet Earth. They invite us to ponder the immense scale of the universe and the intricate ways in which its most powerful events leave their lasting imprint, reaching even to our humble planetary home. From the spectacular fiery aftermath of a dying star, an event we call a supernova, to the swirling, voracious heart of a black hole. These cosmic rays are born from events that defy our earthly comprehension. They are forged in furnaces of unimaginable heat and pressure, accelerated by magnetic fields of immense power. It is as if the universe, in its most dramatic moments, chooses to fling these tiny projectiles across the void, offering us a direct line of communication to phenomena that we, tethered to our world, cannot directly observe. We cannot journey to a supernova remnant and touch it. We cannot approach an active galactic nucleus to feel its energy. But these cosmic rays, they bring a piece of those distant, powerful places right to our doorstep. Imagine, if you will, that each cosmic ray is a tiny, perfectly preserved fossil of an extreme cosmic event. It has traveled for thousands, perhaps millions, or even billions of years, crossing vast swathes of intergalactic space, navigating through nebulae, past stars, and across the gentle currents of cosmic winds, all to deliver its silent, profound message. They are truly the universe's oldest and most persistent couriers, delivering parcels of fundamental information, helping us to piece together the grand puzzle of the cosmos. But how do we even begin to know they are there? How do we perceive these silent whispers from the void, these invisible guests that arrive unannounced? And what precisely are they made of? Are they light? Are they something more tangible? Tonight, as we continue our gentle exploration, we shall slowly, serenely dive into the fascinating history of their discovery, tracing the quiet dedication of the scientists who first sensed their presence, and then gently unravel their fundamental composition, understanding the very essence of these profound cosmic messengers. It is a journey that began with simple curiosity, leading us to profound revelations about our place in the cosmic tapestry. You know, as we gently settle into our understanding of cosmic rays as invisible messengers, let us now turn our attention to their very essence, their fundamental composition. What are these silent bullets made of? These particles that travel across such immense cosmic distances? It is a question that, once answered, begins to paint a clearer picture of their origins and the powerful processes that give them birth. Imagine for a moment the smallest, most fundamental building blocks of matter that you might already be familiar with. At the heart of every atom lies a nucleus, a tiny, dense core. And within that nucleus, we find even smaller particles, protons and neutrons. These are the very substance of stars, of planets, of you and me. And it is these very particles, stripped of their accompanying electrons, that form the vast majority of cosmic rays. Specifically, the primary cosmic rays, those that first arrive from space, are predominantly atomic nuclei. Think of them as bare, naked nuclei, having shed their electron shells as they were accelerated to incredible speeds. And among these nuclei, one particle reigns supreme, the proton. Just like the hydrogen atom, which consists of a single proton and a single electron, is the most abundant element in the universe, so too is the proton the most abundant constituent of cosmic rays. It is estimated that approximately Bifinger gores of all cosmic rays are simply these single positively charged protons. Following protons, the next most common atomic nucleus found within the cosmic ray shower is that of helium, which consists of two protons and two neutrons. So about Bifinger Jove of cosmic rays are helium nuclei. The remaining tiny percentage, less than Bifinger E, is made up of the nuclei of heavier elements. We find traces of carbon, oxygen, iron, and even rarer, heavier elements from across the periodic table. These heavier nuclei, though less numerous, are incredibly valuable to scientists. They are like rare, precious gems within the cosmic stream, each hinting at specific conditions and elemental abundances in their distant birthplaces. Now it is crucial to understand that these are not just ordinary protons or helium nuclei. Oh no, these particles have been accelerated to energies that truly defy our earthly comprehension. Imagine, if you will, a tiny proton smaller than anything you can possibly see, hurtling through the vacuum of space at nearly the speed of light. 99.999% the speed of light, and sometimes even faster in the truly extreme cases. This means that they carry an enormous amount of kinetic energy, far, far beyond anything we can achieve in our most powerful particle accelerators here on Earth. Even those monumental machines designed to smash particles together. The sheer energy of these individual particles is astounding. Some ultra high energy cosmic rays carry the kinetic energy equivalent of a baseball thrown at 8 miles per hour, concentrated into a single infinitesimally small particle. To put that into perspective, It's like taking the force of a powerful athletic throw and compressing it into a single, invisible speck. This immense energy allows them to traverse vast intergalactic distances, bending only slightly in the presence of magnetic fields, arriving at our planet with their profound messages intact. You know, as these primary cosmic rays, primarily protons and helium nuclei, gently encounter Earth-Prime's atmosphere, they do not simply pass through unimpeded. Instead, they interact with the nuclei of nitrogen and oxygen atoms in the air, creating a cascading shower of secondary particles. It is like throwing a single, incredibly energetic pebble into a pond, creating ripples that then create smaller ripples, and so on. These secondary particles include muons, electrons, positrons, and photons, and it is often these secondary particles that we detect here on the ground. So when we speak of cosmic rays, we are primarily referring to these fundamental atomic nuclei, often just bare protons accelerated to incredible velocities and carrying astonishing amounts of energy. Their very composition provides crucial clues, like a cosmic fingerprint, allowing us to begin to understand the violent, powerful processes that are capable of accelerating such tiny particles to such magnificent speeds, preparing us for our next gentle step, understanding how we first became aware of their subtle, silent presence. Having gently understood what cosmic rays are made of, let us now drift back in time to the quiet dawn of their discovery. It is a story not of sudden revelation, but of persistent, gentle questioning of scientists slowly, meticulously piecing together clues from an unseen world. For decades, electricity had been a source of wonder, and scientists had observed that electroscopes, simple devices used to detect electric charge, would mysteriously lose their charge over time when carefully. The prevailing thought was that this discharge was due to natural leakage or perhaps radioactivity within the Earth itself. Imagine a scientist in the early Earth's century carefully sealing an electroscope, watching its delicate leaves slowly fall. This was a puzzle. If everything was perfectly insulated, what was causing this gentle, persistent discharge? Was it a flaw in their instruments or something more profound? The turning point arrived in Ichenjubei Ishur, thanks to the pioneering work of an Austrian physicist named Victor Hess. He was a man of quiet determination, driven by an unyielding curiosity. To investigate the source of this mysterious radiation, Hess undertook a series of daring balloon ascents. Picture him, bundled against the cold, ascending slowly into the sky, carrying his sensitive electroscopes higher and higher above the Earth-Prime's surface. His hypothesis was simple. If the radiation was coming from the Earth, its intensity should decrease as he ascended. But what he found was utterly astonishing, gently overturning all previous assumptions. As his balloons climbed to altitudes of several kilometers heights that were significant for the technology of the time, the rate of discharge in his electroscopes did not decrease. On the contrary, it increased significantly. The higher he went, the stronger the effect became. You know, this was a profound moment of realization. It meant that the source of this penetrating radiation was not the Earth, but something coming from above, from the heavens themselves, something previously unknown constantly bathing our planet. Hess concluded with quiet conviction that there must be an extremely penetrating radiation entering our atmosphere from outer space. He called it Höhenstrahlung, or radiation from above. Later, this would be gently refined and named cosmic radiation, or cosmic rays, a term coined by Robert Millikan in the Ichengeobidarsis. Hess's pioneering work, conducted with simple instruments and immense courage, truly opened a new window onto the universe. He was awarded the Nobel Prize in Physics in Ichengeobidarsis for this profound discovery. His gentle ascents into the sky revealed that our planet is not merely adrift in empty space, but is constantly being touched, gently yet powerfully, by an unseen rain of particles from the cosmos. Following Hess's initial revelation, other scientists, inspired by his findings, began to develop more sophisticated methods to study these elusive particles. Cloud chambers, devices that allow us to visualize the paths of charged particles as they move through a supersaturated vapor, became invaluable tools. Imagine seeing a faint, misty trail like a wisp of cloud, forming as an invisible particle passes through. These visual tracks provided the first tangible evidence of these unseen visitors, allowing scientists to begin to deduce their properties. It was in these cloud chambers that scientists like Carl David Anderson in the Ichengeobidarsis Centers made another astonishing discovery: the positron, the antiparticle of the electron. This discovery of antimatter was a direct consequence of studying cosmic ray interactions, a testament to the profound messages these particles carry, sometimes revealing entirely new facets of fundamental physics. You know, the early history of cosmic ray discovery is a beautiful testament to human curiosity and ingenuity. It began with a seemingly minor anomaly, a slowly discharging electroscope, and, through careful observation and courageous experimentation, led to the realization that our planet is continuously immersed in a silent, energetic symphony originating from the far reaches of the cosmos. These quiet whispers from the void, once merely a puzzling observation, transformed into a profound understanding of our connection to the grand, dynamic universe, paving the way for the sophisticated observatories we use today to listen even more closely. You know, as our understanding of the fundamental nature and historical discovery of cosmic rays gently unfolds, let us now turn our attention to the ingenious methods scientists have devised to listen to these silent messengers from the cosmos. How do we, mere beings on Earth, capture the faint, fleeting signals of particles traveling at nearly the speed of light from unimaginable distances? It is a story of human ingenuity, patience, and a deep desire to comprehend the unseen. You might imagine trying to catch a whisper in a hurricane, or trying to spot a single raindrop in a vast ocean. Detecting cosmic rays presents a similar challenge, yet scientists have developed an astonishing array of sophisticated tools, from the subtle dance of balloon-borne detectors in the upper atmosphere to the colossal, tranquil structures of giant ground-based observatories. Let us begin our gentle journey of detection high above, in the very realm where primary cosmic rays first interact with our atmosphere. Balloon-borne detectors, much like those used by Victor Hess over a century ago, continue to play a crucial role, though they are now far more technologically advanced. Picture a giant, silent balloon slowly ascending through the Earth's atmosphere, carrying delicate instruments designed to sense the first touch of these cosmic visitors. These instruments often contain layers of scintillators, materials that emit a tiny flash of light when a charged particle passes through them. By precisely measuring these flashes and the timing between them, scientists can reconstruct the path and energy of the incoming particle before it fragments into a shower of secondary particles. And so, see, these gentle flights provide us with a direct glimpse of the primary cosmic rays, undisturbed by the atmospheric cascade. As cosmic rays plunge deeper into the atmosphere, they initiate a cascade, a shower of secondary particles that spread out like an invisible fan. It is often these secondary particles that terrestrial detectors are designed to capture. Imagine a cosmic ray hitting an atom in the upper atmosphere, shattering it and creating a shower of new, less energetic particles that continue downwards. One of the most remarkable and visually striking examples of a ground-based observatory is the IceCube Neutrino Observatory, nestled deep beneath the South Pole's pristine ice. While primarily designed to detect elusive neutrinos, IceCube also serves as a magnificent detector for cosmic rays. Picture a cubic kilometer of ice frozen in eternal silence, with thousands of sensitive light sensors, called digital optical modules, suspended within it. When a high-energy cosmic ray, or more precisely, its secondary particles, interacts with the ice, it produces a faint blue glow known as Cherenkov radiation, a kind of sonic boom of light. By mapping these light signals within the vast volume of ice, scientists can reconstruct the energy and direction of the original cosmic ray, almost like listening to the echoes of a distant thunder. It is a testament to the scale of the universe that we need to build observatories of such immense proportions to capture these faint yet profound signal. Other ground-based observatories utilize vast arrays of detectors spread across immense landscapes. The Pierre Auger Observatory in Argentina, for instance, spans an area larger than many cities. Imagine thousands of small, water-filled tanks, each equipped with sensors, spread across a tranquil plain. When a shower of secondary particles from an ultra-high-energy cosmic ray hits these tanks, they create Cherenkov light in the water, which is then recorded. By timing the arrival of these particles at different tanks and by measuring the strength of the signal, scientists can reconstruct the properties of the original cosmic ray with astonishing precision. It is like setting out a vast array of subtle traps, patiently waiting for the universe to send its most energetic visitors. Beyond Earth, space-based observatories offer an even more pristine view. Missions like the Alpha Magnetic Spectrometer, AMS-ER aboard the International Space Station, or the Pamela experiment, orbit above our protective atmosphere, directly sampling the primary cosmic rays before they are altered by atmospheric interactions. These instruments use powerful magnets to bend the paths of charged particles, allowing scientists to determine their charge and momentum, identify their type and energy. Imagine a gentle magnetic net sifting through the cosmic wind, carefully sorting and categorizing each arriving particle. Through these diverse and ingenious methods, scientists are not just passively observing, they are actively listening, carefully interpreting the silent symphony of cosmic rays. Each detection provides another piece of the grand cosmic puzzle, allowing us to map their energies, understand their composition, and, most importantly, begin to trace them back to their distant, powerful origins, a journey we are about to embark upon. As we continue our gentle journey into the realm of cosmic rays, having now understood their composition and how we meticulously detect them, a profound question naturally arises: where do they come from? The universe is vast and full of wonders, but what specific cosmic phenomena possess the incredible power to accelerate these tiny particles to such mind-boggling energies? While some lower energy cosmic rays do originate from within our own solar system, primarily from the sun during its more active phases, the truly energetic ones, those that carry the most profound messages, are undeniably extraterrestrial, emanating from far beyond the comforting confines of our local neighborhood. Let us first turn our gaze towards our own Milky Way galaxy, a swirling, majestic spiral of billions of stars. Within this grand step, one of the most powerful and dramatic events imaginable stands out, as a prime candidate for the acceleration of galactic cosmic rays, the supernova. Imagine a star many times more massive than our sun, reaching the end of its long, luminous life. It has fused lighter elements into heavier ones in its core for billions of years, a gentle, sustained nuclear fire. But eventually, its nuclear fuel runs out. The star can no longer support its own immense weight, and its core collapses inward with astonishing speed. This inward collapse then rebounds outward in a colossal explosion, an event so powerful it can outshine an entire galaxy for a brief period. And this is a supernova, a cosmic fireworks display of unparalleled intensity. But the story does not end with the brilliant flash of light. The aftermath of this explosion, the expanding shell of gas and dust known as a supernova remnant, is a cosmic crucible where cosmic rays are believed to be born and accelerated. Picture a vast, beautiful, yet turbulent bubble of superheated gas, expanding outwards at thousands of kilometers per second, sweeping up interstellar material in its wake. Within this chaotic environment, powerful shock waves are generated. These shock waves are like colossal cosmic accelerators, right? Through a process known as diffusive shock acceleration, charged particles, the protons and atomic nuclei that will become cosmic rays, are repeatedly bounced back and forth across these shock fronts, gaining immense amounts of energy with each pass. It is like a cosmic pinball machine, where the particles are the tiny balls and the shock fronts are the powerful bumpers, imparting more and more kinetic energy until these particles are flung out into the galaxy at nearly the speed of light. This process is incredibly efficient, turning the raw energy of the supernova explosion into the kinetic energy of these tiny, relentless messengers. Supernova remnants are thus considered the primary factories for the vast majority of galactic cosmic rays, those with energies up to about a peta-electron-volt PeV, which is a quadrillion These are the particles that fill our galaxy, gently permeating the vast interstellar medium, occasionally intersecting with our solar system and reaching our planet. They carry the indelible mark of these stellar cataclysms, providing us with a direct link to the dramatic ends of massive stars and the profound cosmic recycling of matter and energy. While supernovae are the leading candidates, other powerful galactic phenomena may also contribute to the cosmic ray population. Pulsars, rapidly rotating neutron stars left behind after some supernova events, possess incredibly strong magnetic fields and can generate powerful electromagnetic winds, potentially accelerating particles. Stellar winds from massive stars, too, might play a role, albeit a smaller one. So, when we speak of galactic cosmic rays, we are often referring to the silent echoes of dying stars, their explosive finales serving as the engines that propel these fundamental particles across the Milky Way. These particles, born in cosmic violence, then embark on incredibly long, peaceful journeys, carrying with them the memory of their fiery birthplaces, offering us insights into the dynamic, ever-changing. They remind us that even in destruction, there is a profound form of creation and communication. Having explored the powerful stellar engines within our own galaxy, that give birth to many cosmic rays, let us now gently expand our view, venturing far beyond the familiar spiral arms of the Milky Way. I, for among the cosmic ray population, there exists an even more mysterious and utterly astonishing subset, energy cosmic rays. These are particles whose energies dwarf even those from supernovae within our galaxy, pushing the very boundaries of known physics, and their origins remain one of the universe's most captivating enigmas. Imagine a single particle, a lone proton, carrying the kinetic energy of a perfectly pitched baseball, or even a tennis ball, but compressed into a speck so small it is beyond human comprehension. These are the ultra high energy cosmic rays, often referred to as UHECRs. They arrive at Earth with energies exceeding an exa-electron volt eV, which is a billion electron volts. The sheer energy of these individual particles is truly mind-boggling, far, far exceeding anything we can ever hope to create in our most powerful laboratories. The greatest mystery surrounding these celestial giants is their birthplace. Unlike their lower energy galactic cousins, these extreme particles cannot be contained within the Milky Way by its magnetic fields. They are simply too energetic. Their paths are almost straight lines across the cosmos, pointing back to their distant origins. This means they must originate from outside our galaxy, from phenomena of unparalleled power in the universe. They're one of the leading candidates for the birthplace of these ultra-highness. Energy messengers is a class of objects known as active galactic nuclei, or AGNs. Picture the very heart of certain galaxies, not a quiet, dormant central black hole, but one that is actively feeding on vast amounts of gas and dust. As this matter spirals inward towards the supermassive black hole, it forms an incredibly hot luminous accretion disk. From this turbulent disk, powerful jets of plasma are often ejected outwards at speeds close to that of light, extending for millions of light years into intergalactic space. These jets are colossal cosmic accelerators, perhaps the most powerful in the entire universe. Imagine a cosmic fire hose spraying energetic particles across the cosmos. Within these powerful jets, and the violent shock waves they create as they plow through the intergalactic medium, particles can be accelerated to energies capable of producing these ultra-high energy cosmic rays. The sheer scale and power of AGNs make them compelling candidates as they possess the necessary energy reservoirs and magnetic field configurations to perform such a monumental feat of acceleration. Another captivating possibility hinting at even more extreme cosmic violence lies in the heart of gamma ray bursts, or GRBs. These are the most powerful explosions in the universe since the Big Bang itself. Picture a colossal cosmic beacon, briefly outshining entire galaxies, emitting a concentrated burst of gamma rays. These short, intense bursts are thought to be associated with the collapse of massive stars into black holes, or the merger of two neutrons. In these fleeting yet unimaginably powerful events, conditions might be ripe for the acceleration of particles to the highest energies observed. They are like cosmic flashbulbs, momentarily illuminating the paths of these ultra-energetic particles. The challenge in pinpointing the exact sources of these UHCRs is immense. While their paths are less bent by magnetic fields than lower energy cosmic rays, they still interact subtly with the cosmic microwave background radiation, the gentle afterglow of the Big Bang, losing some energy over immense distances. This interaction, known as the GZK limit, implies that the most energetic cosmic rays must originate from relatively nearby extragalactic sources within a few hundred million light years. This helps narrow down the search, but the universe is still vast. The study of ultra high energy cosmic rays is a profound journey into the most extreme phenomena in the universe, pushing the boundaries of known physics. They challenge our understanding of particle acceleration and cosmic distances. Each detected UHECR is a precious, silent whisper from the truly extreme, a messenger from processes so powerful they humble our earthly comprehension, urging us to continue listening closely to the grand symphony of the cosmos. As we gently unravel the origins of these silent cosmic messengers, let us now contemplate their profound implications, not just as scientific curiosities, but as subtle yet significant participants in the grand cosmic dance. Cosmic rays, though invisible, weave themselves into the fabric of our existence, influencing everything from the climate of our planet to the very evolution of galaxies. First, let us consider their interaction with our own planet. Our Earth is a vibrant oasis, protected by an invisible shield, its magnetic field and atmosphere. Imagine our planet as a delicate ship sailing through a cosmic storm, and this shield as its valiant, unseen protector. When cosmic rays, particularly the more energetic ones, encounter Earth's magnetic field, their paths are gently deflected, bending them away from the planet's surface. This protective embrace is strongest at the equator, where fewer cosmic rays penetrate directly, and weakest at the poles, where the magnetic field lines converge, allowing more particles to funnel down. This is why auroras, the beautiful dancing lights in the polar skies, are a visible manifestation of these particles interacting with our atmosphere, a gentle reminder of the cosmic ballet happening above us. Those cosmic rays that do penetrate the magnetic shield, then encounter our atmosphere, initiating the cascade of secondary particles we discussed earlier. These secondary particles, including muons, constantly rain down upon us, passing harmlessly through our bodies by the millions every second. You are, at this very moment, being gently permeated by the echoes of distant supernovae and active galaxies, a quiet, continuous interaction with the cosmos. However, beyond this constant, gentle interaction, cosmic rays have real world implications. For astronauts traveling beyond the protective embrace of Earth's atmosphere, cosmic rays pose a significant challenge. Imagine journeying to the Moon or Mars, unprotected by our planet's magnetic field. These highly energetic particles can penetrate spacecraft walls and human tissue, potentially causing cellular damage and increasing cancer risks. Developing shielding for future space missions is a crucial endeavor, underscoring the tangible impact of these invisible cosmic entities on our aspirations for space travel. They are a subtle yet potent reminder that space is not entirely benign. Beyond our immediate vicinity, on a cosmic scale, cosmic rays play a vital, often unseen role in galactic evolution. Imagine a galaxy, a vast cosmic ecosystem. The interstellar medium, the gas and dust between stars, is not empty. It is a dynamic, complex. Cosmic rays permeate this medium, gently ionizing atoms and molecules, influencing chemical reactions, and contributing to the overall pressure of the gas. This ionization can affect the delicate balance within molecular clouds, those vast nurseries where new stars are born. By subtly altering the conditions, cosmic rays can influence the rate of star formation, acting as a gentle yet persistent architect of galactic structures. They are part of the grand cycle of matter and energy that shapes the very architecture of our galaxy. Furthermore, Cosmic rays offer a unique telescope into the universe's most extreme environments. Are Unlike light, which can be absorbed or scattered by interstellar dust and gas, cosmic rays, particularly the most energetic ones, can traverse vast distances relatively unimpeded. They carry direct information about the source itself, allowing us to see processes and conditions that are impossible to replicate in laboratories here on Earth. They reveal the physics of powerful shocks, intense magnetic fields, and extreme particle acceleration, conditions that exist only in the most violent and energetic corners of the cosmos. They are not just messengers, they are probes carrying information about the very physics of the universe's most dramatic events. So cosmic rays are far more than just abstract scientific concepts. They are tangible threads in the cosmic weave, influencing our planet, shaping the very structure of our galaxy, and offering us a unique, profound window into the universe's most powerful mysteries. They remind us that everything is interconnected, from the fiery death of a distant star to the gentle, imperceptible stream of particles passing through you at this very moment. As we draw our gentle exploration of cosmic rays to a close, let us cast our gaze forward towards the shimmering horizon of future discovery. The story of cosmic rays is far from complete. Indeed, we are only just beginning to truly listen to their silent whispers. New generations of observatories, both sprawling across our Earth and soaring gracefully through the silent vacuum of space, are continuously pushing the boundaries of what we can detect and understand. Imagine scientists with renewed vigor and ever more sensitive instruments refining their listening posts. The pursuit of cosmic rays is an ongoing testament to human ingenuity and our unyielding desire to comprehend the universe. Future arrays on Earth will be even larger, even more sensitive, allowing us to capture the rarest and most energetic cosmic rays with greater precision. They will be like vast cosmic nets, cast wider and wider to catch every subtle ripple in the cosmic ocean. One of the most exciting frontiers lies in solving the ultimate puzzle that still shrouds the highest energy cosmic rays, precisely pinpointing their source. As we discussed, these ultra-high energy particles travel almost in a straight line across the cosmos, acting as direct pointers to their birthplaces. However, they are incredibly rare, making their detection a formidable challenge. Future observatories will aim to increase the number of these detections significantly, allowing scientists to create a clearer map of their arrival directions. By correlating these arrival directions with known energetic objects in the universe, the active galactic nuclei, the gamma ray bursts, we might finally unveil the specific cosmic engines responsible for these most extreme phenomena. This breakthrough could unlock entirely new physics, revealing processes we can only theorize about today. It is like trying to find the origin of a faint yet powerful signal in an immense, complex city. The more receivers you have, the better your chances of triangulating the source. Beyond just identifying sources, scientists are actively working on deciphering the subtle flavor of cosmic rays. By meticulously studying their elemental composition at various energies, we can gain deeper insights into the precise conditions within their acceleration sites. Are they rich in iron, suggesting a specific type of stellar collapse? Do they show traces of exotic particles, hinting at physics beyond our current standard model? Each element, each energy level is a unique data point, a precious detail in the grand cosmic narrative. As our understanding grows, Cosmic rays could even become a novel, complementary way to see the universe. For centuries, our primary window to the cosmos has been electromagnetic radiation, visible light, radio waves, X rays, gamma rays. Each wavelength reveals a different aspect of the universe, like different colors on a painter's palette. But cosmic rays offer a fundamentally different perspective. They are matter, not light, carrying unique information about particle acceleration, magnetic fields, and extreme energy processes that light alone cannot fully reveal. Imagine a future where we have a complete multi-messenger picture of the universe. We see the cosmos with light, hear it with gravitational waves, and feel its energetic heart through cosmic rays and neutrinos. Each messenger tells a unique part of the cosmic story, and together they paint a truly holistic and awe-inspiring portrait of existence. Cosmic ray astronomy is poised to become an increasingly vital part of this multi-messenger symphony, revealing entirely new cosmic phenomena that have remained hidden until now. So as the silent rain of cosmic rays continues its unending descent upon our planet, remember that each particle is a message, a whisper from the universe, carrying secrets of its grandest and most powerful events. The future of cosmic ray astronomy is a gentle promise of even deeper understanding, an invitation to continue listening, learning, and expanding our tranquil appreciation for the magnificent dynamic cosmos that embraces us all. As the gentle cosmic dust settles around us, and our journey through the silent symphony of cosmic rays comes to a quiet close, take a moment to simply breathe. You have traveled, in your mind's eye, from the core of exploding stars to the heart of active galaxies, from the silent depths of polar ice to the delicate embrace of Earth's protective shield. You have listened to the whispers of particles that have journeyed for millennia, carrying messages of unimaginable power and profound mystery. These invisible messengers, these cosmic rays, remind us that even as we stand seemingly still on our tiny planet, we are perpetually connected to the vast, dynamic, and breathtaking tapestry of the universe. They are a testament to the ceaseless energy that flows through the cosmos, a quiet reminder that the universe is alive, constantly communicating, if only we learn to listen with gentle curiosity. May this journey leave you with a sense of peaceful wonder, a deepened appreciation for the hidden beauty of the cosmos, and perhaps a new understanding that you are, in every quiet moment, bathed in the profound, silent communication network. Rest now, and let these cosmic messages gently drift through your dreams.